Hello and welcome to this session on Newton's three laws of motion. The man in the picture on the screen in front of you is Sir Isaac Newton, undoubtedly one of the scientists who all physicists today stand on his shoulders. And next to that is the paper which he published, which introduces the three laws of motion which I'm about to discuss. So let's go in numerical order. Newton's first law. Bodies will continue to move with a uniform velocity. Now remember, that includes being stationary unless acted on by resultant force. So if we look at the picture above, what happens, although there's lots of forces being exerted, there is no overall resultant force, so there'll be no motion until that moment in time. Now remember here, this means that if a body changes speed or direction, so speed or direction, both of those inherent parts of velocity, a resultant force must be acting on it. So it's really important there. So it could be traveling at a constant velocity, or this could be stationary. Let's think about static situations here. Balance forces in a static equilibrium. We see these four balls, each of them in a static situation. They're not moving in any way. The first three balls will be undergoing the force of weight, and there'll be an equal and opposite force which is up thrust, and therefore they're floating. And then we have my golf ball, and the golf ball is laying at the bottom of the fish tank, so there will be a normal force pushing up and the weight pushing down. Either way, we have static equilibrium, so there's no resultant force, so these objects remain stationary. We've also got to remember that this law applies when objects are in motion as well. And Newton's first law is the reason why people will fly out of cars if they're not sensibly wearing their seatbelts. And the reason for that is there is a force applied to the car which stops the car. However, as there's been no force applied to the young man flying through the air, it causes him to continue on with exactly the same velocity until a resultant force changes that. So that's why he's flying out of the car there. Newton's second law now. The amount of acceleration that a force produces depends on the mass of the object being accelerated. Is the formal statement. Most people know this as the resultant force equals mass times acceleration, net force. That means that if we know the force, we can work out the mass, we can work out the acceleration, or any one of those other unknowns in an equation. This is quite often what happens. So let's test this out for you. We have a car of a mass 1,000 kilograms. What would be the acceleration in each of those situations? Take a moment to work these out. First one should be 0.5 meters per second squared, with 500 newtons being the resultant force. The second car, we should have a 400 newton resultant force, so I have 0.4 meters per second squared would be the acceleration. And the last example, there's no resultant force, so there'd be no acceleration, 0.0 meters per second squared. Newton's third law, whenever one body exerts a force on a second body, the second body exerts an equal but opposite force on the first body. This is every action has an equal and opposite reaction. But there's some nuances here, and in some ways this is often the most difficult to comprehend. Okay. So, first of all, you might well recognize this if you were a street fighter, in this case, or if you've ever happened to knock a wall or hit a wall anyway, you recognize that the force of A on B is going to be, there's going to be an equal force on B on A in the opposite direction. That is why if you punch a wall, a person, anything, it hurts. Okay, so I recommend not to do that anyway, but that's because there's the equal and opposite force. Now, these equal and opposite forces have a certain nuance, there are certain requirements for them. They must be the same type of force acting on the other object. I think the easiest one to understand here is the space shuttle, space shuttle traveling around planet Earth. And what happens is that for the attraction, gravitational attraction to the center of Earth of the space shuttle, there's also an equal and opposite gravitational attraction of the Earth to the space shuttle. If we look at the car driving, we have the friction of the road on the car and the friction of the car on the road. These are equal and opposite, and notice how they're acting on different bodies. The man pushing the fridge, he's pushing the fridge, and the fridge pushes back with an equal and opposite force. So these are what's known as Newton's pairs. So these are identified as action and reaction forces. However, some people get confused. These rules means that it must be the same type of force. So for instance, the normal force and the weight are not action-reaction pair. You've also got to remember an action and reaction pair need to be working so they don't cause a rotation of any sort. So they have to be working through the same point. So in review, bodies will continue to move with a uniform velocity, including stationary, unless acted on by a result. So that means if a body changes speed or direction, a resultant force must have been acting on it. Newton's second law, we recognize that F equals ma. Resultant force is equal to the rate of change of momentum. So when we consider momentum in more detail, we'll come back to Newton's second law to prove that point. And finally, Newton's third law, every force has an equal and opposite force acting on it on another object. Hopefully that's given you a quick review of Newton's 3 laws of motion.